Welcome to Lesson 7, where we will explore the fascinating world of alcohols and phenols. These compounds are integral to both organic chemistry and everyday life, playing critical roles in biological systems, industrial applications, and household products. Understanding their structure, properties, and reactions is essential for a deeper comprehension of organic chemistry. Throughout this lesson, we will explore the preparation methods for both alcohols and phenols. We will also discuss the various reactions that alcohols and phenols undergo, such as oxidation, substitution, and elimination reactions. By understanding these mechanisms, we can predict the products of such reactions and appreciate the versatility of these compounds in synthetic organic chemistry. As we journey through this lesson, keep in mind the broader applications and implications of alcohols and phenols in both chemistry and daily life. Whether it's the ethanol in alcoholic beverages, the methanol used as a solvent, or the phenolic compounds found in essential oils and pharmaceuticals, these substances are all around us, showcasing the remarkable diversity and utility of organic molecules. Let's go to the next slide and look at an outline of topics for the lesson. In Part 1 of the lesson, we begin with an overview of the functional groups and natural occurrences of alcohols and phenols. Alcohols, with their hydroxyl group attached to a saturated carbon, and phenols, with a hydroxyl group bonded to an aromatic ring, play vital roles in both nature and chemistry. Next, we cover the nomenclature and physical properties of these compounds. We'll discuss naming conventions and how the hydroxyl group affects properties such as boiling point and solubility. We then move on to the acid/base chemistry of alcohols and phenols. This section will focus on their acidity, resonance stabilization in phenols, and deprotonation reactions. In the second part of the lesson, we explore methods for preparing alcohols, including substitution and addition reactions. We'll look at reaction mechanisms and how nucleophiles and electrophiles interact to form alcohols. Next, we will discuss the dehydration of alcohols to form alkenes, emphasizing the reaction's significance in synthetic chemistry. We then examine the conversion of alcohols into alkyl halides, highlighting its importance for subsequent reactions. Finally, we cover the oxidation of alcohols, detailing how primary, secondary, and tertiary alcohols are oxidized to form aldehydes, ketones, and carboxylic acids. Throughout the lesson, we will integrate theoretical knowledge with practical examples, illustrating the significance of alcohols and phenols in both the laboratory and everyday life. By the end, you will have a solid understanding of these compounds, their reactions, and their importance in organic chemistry. Alcohols are defined by the presence of a hydroxyl group attached to a saturated carbon atom. This hydroxyl group is a defining feature that significantly influences the chemical and physical properties of alcohols. Two example alcohols are shown below: ethanol and cyclopentanol. In both cases, we can see the presence of the key functional group, the hydroxyl group, connected to an sp3 hybridized carbon atom. Ethanol, being acyclic and fully saturated, can be referred to as an aliphatic acyclic alcohol, whereas cyclopentanol would be described as a cyclic aliphatic alcohol. Hydroxyl groups are extremely common in nature, playing crucial roles in a variety of biological molecules. For instance, cholesterol, which is vital for the biosynthesis of steroids, features a hydroxyl group. Similarly, cholecalciferol, or vitamin D3, contains a hydroxyl group and is essential for regulating calcium levels to maintain strong bones. Another notable example is chloramphenicol, an antibiotic isolated from the bacterium Streptomyces venezuelae, which contains multiple hydroxyl groups contributing to its potent activity against typhoid fever. These examples highlight the significance of hydroxyl groups in both biological and pharmaceutical contexts, demonstrating their essential role in the structure and function of natural compounds. Phenols, like aliphatic alcohols, also possess the hydroxyl group in their structure, but they differ significantly in other ways. Let's go to the next page and examine the characteristic structural features that define the phenol functional group. Phenols are a distinct class of compounds, characterized by a hydroxyl group directly attached to a benzene ring. This structural feature significantly influences their chemical properties and reactivity compared to alcohols. The parent compound of this class is phenol itself, which serves as a fundamental building block for more complex molecules. Phenols are prevalent in various natural and synthetic compounds, often contributing to their biological activity. For instance, dopamine is a neurotransmitter critical for brain function, particularly in regulating mood and movement, and is deficient in Parkinson's disease. It features a hydroxyl group on the benzene ring, classifying it as a phenol. Uracils are another example, found in the leaves of poison ivy and poison oak. These compounds cause skin irritation upon contact, highlighting the potent biological effects of phenolic compounds. Capsaicin, the active component in chili peppers, responsible for their spicy flavor, also contains a phenol structure. This molecule interacts with sensory receptors, producing the characteristic heat sensation. Lastly, tetrahydrocannabinol is the psychoactive compound produced in the cannabis plant. Its phenolic structure is essential for its interaction with cannabinoid receptors in the brain, leading to its psychoactive effects. Cannabinoids belong to a broader class of organic molecules known as terpenes, which are renowned for their diverse biological activities, intricate biosynthesis pathways, and extensive study in organic and biochemistry. It might be surprising to many that cannabinoids are not only found in cannabis, but are also produced in other plants such as sunflowers, coneflowers, and tea trees. These compounds play significant roles in the plant's ecological interactions and offer a wide range of potential therapeutic applications. These examples illustrate just a few of the diverse roles that phenolic compounds play in nature and their significant impact on both biological processes and human experiences. Now that we have looked at the defining features of alcohols and phenols, let's turn our attention to their organic chemistry. So that we can communicate their structure and reactivity more precisely with each other, we'll start with their nomenclature on the next page. Naming alcohols requires only a few small changes to our current approach. To begin, we need to identify the parent chain. As before, the parent chain will be the longest continuous chain of carbon atoms. However, it is now crucial to ensure that this chain includes the hydroxyl group, as this determines the base name of the alcohol. We'll look at this in detail on the next page with a few examples. Next, we need to learn a new suffix for the alcohol functional group. The suffix used for alcohols is OL. To apply this suffix, modify the name of the parent alkane by changing the E suffix to ol, indicating the presence of an alcohol. Pentane, for example, becomes pentanol when a hydroxyl group is attached to the molecule. We also need to modify our numbering scheme to account for the location of the hydroxyl group. The carbon chain must be numbered starting from the end closest to the hydroxyl group, to ensure that the hydroxyl group receives the lowest possible locant number. This prioritization is crucial for accurate naming. As before, the position of any substituents on the carbon chain must be identified. These substituents are then named and listed in alphabetical order in the compound's name. For example, consider pentane, which has a base name derived from its 5-carbon chain. When a hydroxyl group is attached to the first carbon atom, the compound is named 1-pentanol. This numbering ensures that the hydroxyl group receives the lowest possible number, underscoring its importance in the nomenclature. If there are additional substituents, they would be named and positioned according to this numbering system, and listed alphabetically in the compound's name. This methodical approach to naming alcohols allows for clear and precise communication of their structures, facilitating understanding and discussion in organic chemistry. Let's look at a few of these points in more detail to ensure we understand how to apply them in context. As mentioned, when naming alcohols, the parent chain must include the hydroxyl group, even if it means selecting a shorter chain than the longest one available. This ensures that the base name of the alcohol reflects the presence of the hydroxyl group, even if it is a shorter chain than another candidate on the structure. To see how this works, the structure shown below contains an 8-carbon chain and a 6-carbon chain. The hydroxyl group is connected to the 6-carbon chain, which means that, for naming purposes, the parent alkyl prefix for this compound is hex rather than octane. Even though hex represents a shorter chain of carbon atoms, it takes a higher priority in the selection of the parent name, due to the presence of the hydroxyl group. Additionally, when numbering the carbon chain, it is essential to assign the lowest possible number to the carbon atom bonded to the hydroxyl group. This prioritization ensures accurate and systematic naming. For instance, if the hydroxyl group is closer to one end of the chain, numbering should start from that end to give the hydroxyl-bearing carbon the lowest possible number. In the example shown, 2 functional groups are present. When we learned about the nomenclature of alkenes, we learned to assign the lowest possible location numbers to the first carbon of the C-C double bond. If a hydroxyl group is present, however, the numbering scheme is modified due to the higher priority of the hydroxyl compared with the alkene functional group. As the example shows, we would number the parent chain by starting at the end closest to the hydroxyl group, rather than the alkene. This approach avoids errors and ensures consistent nomenclature across different compounds. The next step, after deriving the parent name and assigning location numbers, is to actually assemble the name. We will follow the same principles as before, listing out substituents in alphabetical order, but we also need to include the location number for the hydroxyl group in our suffix. Let's go to the next page and examine how that works. When naming alcohols, one important aspect to consider is the placement of the locant for the hydroxyl group. The locant indicates the position of the hydroxyl group on the carbon chain, and can be placed in 2 acceptable positions within the name of the compound. This flexibility ensures that the structure of the compound is clearly communicated. The locant for the hydroxyl group can be positioned either just before the parent name or just before the ol suffix. Both conventions are correct and widely accepted in IUPAC nomenclature. For example, consider a molecule where the hydroxyl group is attached to the 3rd carbon of a pentane chain. This molecule can be named in 2 ways. First, it can be named 3-pentanol, with the locant 3 placed just before the parent name pentanol. This format clearly indicates that the hydroxyl group is on the 3rd carbon of the pentane chain, and is straightforward and commonly used. Alternatively, it can be named pentan 3-ol, with the locant 3 placed just before the ol suffix. This method also accurately conveys the position of the hydroxyl group, maintaining the same clarity and precision. Both naming conventions provide the same essential information about the compound's structure, ensuring that the position of the hydroxyl group is clearly indicated. The choice between these 2 formats often comes down to personal preference or regional usage, but both are correct and accepted in scientific communication. Understanding these conventions allows chemists to effectively communicate the structures of alcohols, facilitating clear discussions and reducing the risk of misunderstanding. This flexibility in nomenclature ensures that the names of alcohols are both precise and universally understood, regardless of the specific naming format used. Now that we have looked at the nomenclature of acyclic alcohols, let's turn our attention to cyclic alcohols, and a few common names for alcohols as well. When naming cyclic alcohols, the hydroxyl group is always assigned to carbon 1. This rule simplifies the nomenclature process by providing a clear starting point for numbering the carbon atoms in the ring. For example, in cyclopentanol, the carbon bearing the hydroxyl group is designated as carbon 1. Numbering then proceeds around the ring in the direction that gives the other substituents the lowest possible numbers. In the compound R3,3, dimethylcyclopentanyl, the hydroxyl group is on carbon 1, and the methyl groups are on carbons 3 and 3. In addition to systematic names, some alcohols are commonly known by their traditional names, which are frequently used in both academic and industrial contexts. These common names often originate from historical or traditional sources, and provide an alternative way to refer to these compounds. For example, isopropyl alcohol is the common name for 2-propanol, highlighting the presence of the hydroxyl group on the second carbon of a 3-carbon chain. Similarly, tert-butyl alcohol, known as 2-methyl-2-propanol in systematic nomenclature, features a hydroxyl group on a carbon atom bonded to 3 other carbon atoms. Benzyl alcohol, also known as phenylmethanol, consists of a hydroxyl group attached to a carbon that is connected to a benzene ring. Understanding both systematic and common naming conventions allows chemists to communicate effectively across different contexts. The use of common names is particularly prevalent in industrial applications and everyday language, while systematic names provide precision and clarity in scientific literature. By being familiar with both naming systems, chemists can ensure clear and accurate communication, whether discussing the properties, reactions, or applications of alcohols. As we continue, on the next page, we will examine the classification of alcohols based on the substitution pattern of the carbon atom where the hydroxyl group is attached. This classification is crucial for understanding the reactivity and properties of different types of alcohols. Alcohols can be classified based on the substitution pattern of the carbon atom to which the hydroxyl group is attached. This classification helps us understand the reactivity and properties of different types of alcohols. In primary alcohols, the carbon bearing the hydroxyl group, known as the alpha carbon, is attached to only one other carbon atom. This configuration makes primary alcohols less sterically hindered and often more reactive in certain types of chemical reactions. An example of a primary alcohol is ethanol, where the alpha carbon is bonded to one carbon and 2 hydrogen atoms. Secondary alcohols have the hydroxyl group attached to a carbon atom that is bonded to 2 other carbon atoms. This increased substitution on the alpha carbon alters the reactivity compared to primary alcohols. For instance, isopropanol is a secondary alcohol, with the hydroxyl-bearing carbon connected to 2 other carbon atoms and 1 hydrogen atom. Tertiary alcohols feature a hydroxyl group attached to a carbon atom bonded to 3 other carbon atoms. This configuration provides significant steric hindrance, impacting the reactivity of tertiary alcohols in various chemical reactions. An example of a tertiary alcohol is tert-butanol, where the alpha carbon is bonded to 3 other carbon atoms. Understanding the classification of alcohols is crucial for predicting their behavior in different chemical contexts, such as reactions and synthesis pathways. Having completed our discussion on the nomenclature and classification of alcohols, we will now turn our attention to the nomenclature of phenols. While similar to alcohols, phenols have distinct structural characteristics due to the presence of an aromatic ring, which influences their chemical properties and reactivity. Let's proceed to explore how these differences affect the naming conventions for phenols. When naming phenols, the process shares similarities with alcohol nomenclature, but there are key differences due to the presence of an aromatic ring. When a hydroxyl group is attached directly to a benzene ring, the parent name of the compound is phenol. This serves as the base name from which further modifications are derived. Consider the simplest phenol, where the hydroxyl group is directly attached to the benzene ring. This compound is simply called phenol. The naming becomes more complex when additional substituents are present on the benzene ring. For example, in 4-chloro-2-nitrophenol, the parent compound is phenol, and we identify the positions of the substituents relative to the hydroxyl group. Here, a chlorine atom is attached to carbon 4, and a nitro group is attached to carbon 2. The positions of these substituents are indicated by numbering the carbon atoms in the benzene ring, starting from the carbon bearing the hydroxyl group, and proceeding in a manner that gives the substituents the lowest possible numbers. Substituents are named according to their relative positions from the hydroxyl group, using the lowest locants possible to ensure clarity and precision in the compound's name. This systematic approach allows for an accurate description of the molecule's structure, facilitating communication and understanding within the chemical community. Having completed our discussion on the nomenclature of phenols, we will now transition to exploring the physical properties of alcohols. Understanding these properties is crucial for predicting the behavior of alcohols in various chemical contexts, including their boiling points, solubility, and interactions with other molecules. Let's move on to examine how the presence of the hydroxyl group influences these physical characteristics. The presence of the hydroxyl group in alcohols significantly influences their physical properties. We will look at several key characteristics that distinguish alcohols because of the presence of this functional group from other types of organic compounds. One of the most notable effects of the hydroxyl group is on the boiling point of alcohols. The hydroxyl group enables alcohols to form hydrogen bonds, a type of strong intermolecular force. Hydrogen bonding occurs when the partially positive hydrogen atom of one molecule interacts with the partially negative oxygen atom of another. This interaction requires considerable energy to break, resulting in much higher boiling points for alcohols compared to alkanes or haloalkanes of similar molecular weight. To illustrate this, let's compare the boiling points of ethane, chloroethane, and ethanol. Ethane, a simple alkane with no significant intermolecular forces other than van der Waals forces, has a boiling point of -89 degrees Celsius. Chloroethane, which has a slightly polar carbon-chlorine bond, has a higher boiling point of 12 degrees Celsius due to dipole-dipole interactions. However, ethanol, which can form hydrogen bonds because of its hydroxyl group, has a significantly higher boiling point of 78 degrees Celsius. This stark difference highlights the impact of hydrogen bonding on the physical properties of alcohols. Next, we will examine how the balance between hydrophobic and hydrophilic regions in alcohols affects their miscibility with water. This balance is an important factor in determining the practical applications of different alcohols, particularly in biological and industrial settings. The solubility of alcohols in water is greatly influenced by the balance between their hydrophobic and hydrophilic regions. This balance determines whether an alcohol is miscible with water or not. Alcohols with 3 carbon atoms or fewer are generally miscible in water. These shorter chain alcohols have a hydroxyl group that can form hydrogen bonds with water molecules, facilitating their solubility. For example, methanol, ethanol, and propanol all dissolve readily in water due to the strong hydrogen bonding interactions between the hydroxyl group and water molecules. The small hydrophobic region, the alkyl chain, does not significantly hinder the solubility. On the other hand, alcohols with longer carbon chains have reduced solubility in water. As the length of the carbon chain increases, the hydrophobic character of the molecule becomes more pronounced. This larger hydrophobic region disrupts the hydrogen bonding network with water, making it more difficult for the alcohol to dissolve. For instance, hexanol, with its 6-carbon chain, has a much lower solubility in water compared to ethanol. The extensive hydrophobic region of hexanol interacts poorly with water, thus impeding its ability to mix readily. Understanding the balance between the hydrophobic and hydrophilic regions in alcohols is essential for predicting their behavior in aqueous environments. This knowledge is particularly important in applications such as solvent selection, pharmaceuticals, and biochemical processes, where the solubility of alcohols can impact their effectiveness and functionality. As we continue our exploration of alcohols and phenols, we will next examine their antibacterial properties. Because the hydrophobic and hydrophilic region of alcohols strongly affect their solubility, this structural feature also plays a crucial role in the biological activity of these compounds. Let's move on to see how this balance influences the antibacterial potency of alcohols. The antibacterial potency of an alcohol is significantly influenced by the size of its hydrophobic group. To effectively kill bacteria, an alcohol must strike a balance between its hydrophobic and hydrophilic properties. This balance determines its ability to travel through aqueous media and penetrate microbial membranes. Alcohols with larger hydrophobic regions are more effective at disrupting microbial cell membranes. These regions allow the alcohol to embed into the lipid bilayer of the bacterial membrane, leading to cell lysis and death. However, the alcohol must also retain enough water solubility to diffuse through aqueous environments and reach the bacteria. The graph on the slide illustrates how the antibacterial potency of alcohols changes with the length of the alkyl chain. As the chain length increases, the hydrophobicity also increases, enhancing the ability to penetrate bacterial membranes. However, there is an optimal chain length where the antibacterial activity is maximized. Beyond this point, excessive hydrophobicity reduces the alcohol's solubility in water, decreasing its overall effectiveness. Hexylresorcinol is a prime example of an alcohol with effective antibacterial properties. It features a balanced combination of hydrophobic and hydrophilic regions, making it an effective antibacterial and antifungal agent. The hexyl group provides sufficient hydrophobic character to penetrate microbial membranes, while the hydroxyl groups ensure adequate solubility in aqueous environments. Understanding the relationship between the structure of alcohols and their antibacterial properties is crucial for developing effective antimicrobial agents. The ability to tailor the hydrophobic and hydrophilic balance allows for the optimization of alcohols for specific applications, enhancing their efficacy in medical and industrial contexts. Next, we will explore the acidity of alcohols and phenols, examining how their chemical structure influences their behavior as acids. This understanding will further inform how we utilize these compounds in various chemical reactions and applications. Alcohols and phenols exhibit unique acidic and basic properties due to the presence of the hydroxyl group. Understanding these properties helps us predict their behavior in various chemical reactions. Alcohols are weak Brunstad acids, with a pKa value of approximately 15. This indicates that they do not easily donate their hydrogen ion or proton. To deprotonate an alcohol, a strong base is required. When an alcohol is deprotonated, it forms its conjugate base, known as an alkoxide ion. In the diagram illustrating the deprotonation of an alcohol, we see a curved arrow starting from the oxygen of the hydroxyl group, indicating the lone pair of electrons on oxygen. This arrow points towards the hydrogen atom, showing the formation of a bond between the oxygen and hydrogen, which results in the loss of the proton. Another arrow shows the electrons from the OH bond moving to the oxygen, resulting in the negatively charged alkoxide ion. Phenols, on the other hand, are slightly more acidic than alcohols, due to the resonance stabilization provided by the aromatic ring. When a phenol loses a proton, it forms a phenoxide ion, which is stabilized by the delocalization of the negative charge over the aromatic ring. The deprotonation reaction of phenols is similar to that of alcohols. The diagram shows a curved arrow from the oxygen's lone pair to the hydrogen, and another arrow from the OH bond to the oxygen, forming a phenoxide ion. The resonance structures of the phenoxide ion are shown, illustrating how the negative charge is delocalized over the aromatic system, which stabilizes the ion. Alcohols can also act as weak Brunstad bases. They can accept protons from strong acids to form their conjugate acids, known as oxonium ions. The diagram illustrating the protonation of an alcohol shows a curved arrow from the lone pair of electrons on the oxygen to a proton, H+, resulting in the formation of an oxonium ion. The oxonium ion has a positive charge on the oxygen, due to the addition of the proton. Let's go to the next page and look at the deprotonation of alcohols, to generate their conjugate bases, which as mentioned, are called alkoxides. As we noted on the previous page, alcohols are considered weak Brunstad acids, with a pKa value of approximately 15. This means they do not readily donate their proton, and require a strong base to be deprotonated. A commonly used strong base for this purpose is sodium hydride, which efficiently generates the corresponding alkoxide ion from an alcohol. The reaction mechanism involves the alcohol reacting with sodium hydride. Sodium hydride serves as a base, donating its hydride ion, represented as an H-, due to the non-bonding electron pair on the atom, which forms a covalent bond with the proton from the alcohol, producing hydrogen gas. This process results in the formation of sodium ethoxide from ethanol and sodium hydride. Another method to generate alkoxides is by using alkali metals, such as sodium or potassium. When an alcohol reacts with an alkali metal, the metal donates an electron to the oxygen of the hydroxyl group, forming an alkoxide ion, and releasing hydrogen gas. The reaction is represented in the diagram, where ethanol reacts with sodium metal, to form sodium ethoxide and hydrogen gas. The formation of the alkoxide ion involves the loss of a proton from the alcohol, stabilized by the metal cation. These reactions are fundamental in organic synthesis, as alkoxides serve as strong bases and nucleophiles in various chemical reactions. We utilized various alkoxides as bases and nucleophiles, for example, in substitution and elimination reactions of alkyl halides. Because alkoxides are strong bases, they are quite reactive, and are typically freshly made just before they are used, in order to get the best yields in a reaction. The methods shown here illustrate several methods that are used, in the laboratory and industrial settings, to prepare these reagents when they are needed. Next, we'll explore how the structure of alcohols and phenols influences their reactivity, focusing on electron withdrawing and electron donating groups, and their effects on acidity. This will provide deeper insights into how molecular structure impacts chemical behavior. Electron withdrawing substituents can significantly increase the acidity of alcohols and phenols through inductive effects. These effects occur when electronegative atoms or groups withdraw electron density through the sigma bonds of a molecule, stabilizing the negative charge on the conjugate base, and thereby increasing the compound's acidity. For instance, consider ethanol and trichloroethanol. Ethanol has a pKa value of approximately 16, reflecting its weak acidity. In contrast, trichloroethanol, which has 3 chlorine atoms attached to the carbon, adjacent to the hydroxyl group, has a pKa value of approximately 12.2. The electron withdrawing effect of the chlorine atoms stabilizes the negative charge on the alkoxide ion formed after deprotonation, making trichloroethanol a stronger acid than ethanol. The table shown on the slide lists the pKa values of various alcohols and phenols in aqueous solution, highlighting how the presence of different substituents affects their acidity. For example, phenol has a pKa of approximately 10, making it more acidic than ethanol. This increased acidity is due to the resonance stabilization of the phenoxide ion, formed upon deprotonation. Further down the table, we see para-nitrophenol and picric acid, with even lower pKa values of 7.2 and 0.25, respectively. The presence of nitro groups, which are strong electron-withdrawing substituents, significantly increases the acidity of these compounds. Understanding how electron-withdrawing substituents affect the acidity of alcohols and phenols is crucial for predicting their reactivity and behavior in various chemical environments. This knowledge is particularly important in designing compounds for specific applications, such as pharmaceuticals and agrochemicals, where the acidity can influence the compound's activity and stability. That concludes the first part of this lesson. Next, we will explore the methods for preparing alcohols, focusing on substitution and addition reactions. This will provide insight into the synthetic strategies used to produce these important compounds in both laboratory and industrial settings. See you in the next video. Thanks for watching, and I look forward to seeing you in the next video.